So for introduction, this is our overview. This project develops an automated control system for a vertical farm aquaponic greenhouse using Arduino Uno in Tinkercad simulation. The system automatically monitors and controls temperature, humidity, irrigation, and water circulation to maintain ideal conditions for plant and fish growth. Structured C++ programming is applied to ensure efficient, modular, and well-documented code with proper interfacing of sensors and actuators. Next, we move on to problem statement. Traditional farming faces challenges such as limited space or land and unstable climate conditions. Therefore, vertical aquaponic farming acts as an alternative or a modern solution, but it still requires constant monitoring of temperature, humidity, and water levels, which are difficult to manage manually. Thus, an automated monitoring and control system is needed. Our project uses Arduino and C++ to develop a system that responds automatically to environmental changes in a vertical aquaponic greenhouse. In this project, we have 4 objectives, which are to apply structured programming for sensor actuator interfacing, to design a system to maintain stable environmental conditions, to implement logic for irrigation, ventilation, and water circulation, and to provide safety responses and user alerts through displays or indicators.
Next, we go through the flowchart. This is the main flowchart, which is a combination of 3 different functions. To summarize, this system continuously runs an Arduino to monitor 3 key elements. It first checks the temperature, displaying warnings with colored LEDs, blue for cold, red for hot, or green LED for optimal range. And then number 2, it then checks humidity, automatically controlling a fan to turn on if the humidity is high or off if it's low. Finally, it checks the water level, sounding a buzzer and controlling a valve to alert the user and correct levels if the water is too high or too low, ensuring the system returns to the beginning to continuously monitor the environment of the hydroponic system.
So this slide shows our input-output list, basically all the components we use in the system and how they are connected to the microcontroller. So first, we have our input components, which is the potentiometer, the temperature sensor, and the ultrasonic sensor. So these all send data into the system through analog or digital input pins. So next, we have the output components, which is the LED indicator, the motor driver, the micro servo, the piezo, and the LCD display. So these respond based on the program and are connected to digital output pins or the I2C. So overall, this table summarizes the component type, its operating range, and which pin each device use, making troubleshooting and programming easier.
Now moving on to the code. So firstly, we include all the required libraries, which are libraries for I2C LCD and also microservo. After that, we define pins and variables that we are going to use in this code to monitor the 3 aspects, which are humidity, water level, and also temperature. Not to forget, we also set the LCD address so that it may only print on 16 rows and 2 columns. Next, we move on to void setup, where we set up or we configure all the variables and pins that we defined before this into either input or output. We also initialize the LCD, we turn on the backlight, and also print a simple message to make sure that the LCD is working.
Hello everyone, my name is Kenny Steve, and now I'll be talking about the codes that we use to troubleshoot any system failure that occurs in our project. First, let's look at the humidity sensor failure case. The name of the function is system reset. So what it does is basically when the humidity sensor faces any error, the LCD will display error message on the first row, and on the second row, it will display the humidity sensor, indicating that the humidity sensor is the one that faced error. And for safety measure, we ensure that the fan, which is represented by the DC motor, is turned off when any error occurs with the humidity sensor. Other than that, an error message saying that the humidity sensor has failed and initiating reset will also be printed onto the serial monitor. This tells the user which sensor has phase error. And it will delay for 1 second, and the system will initiate itself, which means it will run the setup function. And after this, if the humidity sensor still face any error, this system reset function will keep repeating itself, keep running until the error faced by humidity sensor is resolved. Secondly, let's look at the temperature sensor failure case. Similarly, we use the same similar name. This function name is called system reset 2. And similarly, what it does is the LCD will display error message on the first row and then TMP sensor on the second row, indicating that the TMP sensor, in this case, it's the TMP36 sensor that has phase error in our system. And when error happens with the TMP sensor, all LED, red, green, and blue LED, which are the outputs for TMP36 sensor, will light up. And this gives additional signal to users showing that the TMP sensor has faced error. And after that, serial monitor will print the message saying temperature sensor has failed. And after that, it will run the setup function again until the error faced by TMP36 sensor has resolved. Lastly, let's look at the water level sensor failure case. We basically use the same principle as the previous two. The name of the function is system reset 3, and it will print error message on the first row of LCD and ultrasonic on the second row, indicating that the ultrasonic distance sensor has phase error. We also ensure that the valve is turned off when any failure occurs with the ultrasonic sensor. The for loop function here that we use to turn off the valve, to close the valve, is basically the same code we use to close the valve when the water in the fish tank is at optimal or low level. After that, the serial monitor will print the error message saying the water level sensor has failed, and it will run the setup function again. And similarly, if the water level sensor still face any error, it will rerun this code again and again until the issue faced by water level sensor is resolved.
So now, this slide shows the coding for humidity and temperature system. So on the left side, we can see the coding for humidity sensor. So the code reads the potentiometer value and converts it into a percentage and displays it on the LCD. So based on the value, the fan will turn on during high humidity and turn off when humidity is low or at an optimal range. So on the right side is the coding for temperature system. So the code reads the TMP36 sensor, which converts the analog value into degrees Celsius, and it prints the temperature to the serial monitor. So just like the humidity part, it also checks for abnormal sensor values to ensure the system is safe. So overall, this program continuously reads both sensors, update the display, and control the output devices automatically.
This section of the code first takes the current temperature and display it on the LCD. It then uses simple if-else if statement to control our warning system. So when the temperature falls within the optimal range between 18 and 24 degrees, only the green LED is lit. If it's too hot or too cold, the code triggers the blue LED or the red LED respectively, while displaying a corresponding warning message on the screen. Next is the water level. For water level, we utilize an ultrasonic sensor. The code emits a sound pulse and measures the time it takes to return, give us the duration. The duration is converted into physical distance using the speed of sound formula, and then subtract from the total tank height to give us the actual water level. Most importantly, we have a critical sensor error check. If the calculated level is outside the reasonable range, for example less than 50 or greater than 380, the code immediately uses return to skip the loop iteration. This ensures the control system, the valve, and buzzer never execute commands based on potentially faulty sensor data. This setup guarantees accurate feedback and safe automatic operation.
Let us continue the explanation for water level sensor. These the codes to explain the conditions for water level sensor. If the water level is too low, the buzzer will produce noise to alert surrounding user. The LCD display low to indicate that the water level is low. And this for loop is used to close the valve and ensure a smooth movement of the servo motor, which is used to represent a valve. And then, if the water level is between 150 to 300, it is considered an optimal water level. Therefore, the same thing will happen. The valve will be closed to ensure that water does not flow up. But if the water level is too high, in this case, above 300, the buzzer will once again produce noise to alert the user, and the LCD will display high, indicating a high water level in the fish tank. And then the for loop just now, we modified it. Instead of closing the valve, we will open the valve to discharge water so that the water in the fish tank will overflow. And then this is basically the entire system. After that, it will rerun again from the top after a 1 second delay. Now I'll explain the circuit that we use for our project. Let's start the simulation. And let's start with the ultrasonic distance sensor. This is the sensor that we use to measure the water level in the fish tank. So now it is working in optimal condition. So it will display here optimal water level, and water level will also be printed onto the serial monitor. If the water level is too low, like this, it will display low water level in the LCD and in the serial monitor. As you can hear, the piezo will also produce noise to alert user that the water level in the fish tank is low. Similar thing happens when the water level is high. It will display high water level here, and you can see that the servo motor just turned, and this replicates the action of a valve being open to discharge water so that the water in the fish tank will not overflow. And when it returns to optimal condition, the servo motor will turn again, replicating the action of the valve being closed to maintain the water inside the fish tank. Now, when this sensor detects a water level that is too high, such as this one, the LCD will display error message. Ultrasonic sensor has faced error. Same thing happens here in the serial monitor. Now, let us move on to the humidity sensor, which is represented by a potentiometer. Now, it is currently working in normal condition, low humidity. When it is in optimal humidity, it will display optimal humidity over here, and the same thing happen here in the serial monitor. The humidity percentage will be displayed. But when the humidity is high, display high humidity, and you can see that the DC motor has started to run. This replicates the action of a fan being started. It will blow away the humid air in the surroundings, and this gives space for new air to replace the removed air in the surroundings. This basically reduces the humidity in the surrounding environment. But when the humidity is at 0% or 100%, which is impossible to happen, we classified it as an error for the humidity sensor. And as you can see, when it's at 0 or 100, the LCD will display error message right after here. Same thing happens here in the serial monitor. That's all for the humidity sensor. And now let's move on to the temperature sensor. It's now 25 degrees Celsius. The temperature is now considered high. The red LED will light up. When it's considered optimal, LCD will display optimal temperature, and green LED will light up. The temperature will also display in the serial monitor. When it's in low temperature, too low for plants in the greenhouse, not this one. Low temperature, LCD will display low temperature, and the blue LED will light up. But when the temperature is too high or too low, let's try too high, it will indicate an error in the temperature sensor. And as you can see, as output, all LEDs will light up, giving alert to user that the temperature sensor has encountered error. The LCD will also display the error message. Temperature sensor has encountered error, and the same thing will happen here in the serial monitor. So that's all about the sensor. This 9-volt battery is used to power this DC motor because the 5-volt pins from the Arduino is not enough to produce, it just cannot produce enough current to power up this DC motor safely. Therefore, a 9-volt battery is used to power up this DC motor. But to incorporate this 9-volt battery into this circuit, the H bridge motor driver is required, which it acts as a crucial interface for this 9-volt battery and this Arduino to work properly and safely, so that still can function, nothing gets damaged, and the DC motor can be used normally.
To conclude, this project successfully allowed us to apply C++ and Arduino to automate a complex vertical aquaponic system. We didn't just build a device, we mastered a process from flowchart and Tinkercad simulation right through the final C++ code. The main takeaway is our ability to transition from concept to a functional engineering solution. We learn structured programming while creating an automated system that controls temperature, humidity, water, and ventilation, providing how Arduino can be used to solve real-life challenges in sustainable farming. Thank you.